Okay, I'm Rick Fleeter, and I'm going to talk first about Microspace, basically what it is. Okay, how else does this transportation system affect the satellite design, right? Well, of course, the mass, the volume. Why do we have CubeSats? Because we have CubeSat launchers. So look, if you want to get launched, guy, 10 centimeters, 10 centimeters, 10 centimeters. Otherwise, no P-pod, no launching, right? So you can't just, one of the reasons I got into spacecraft design was I loved the idea that you had all this freedom. With an airplane, you got the two wings, the two main wings, and you got horizontal stabilizer, vertical stabilizer, fuselage, some sort of propulsion system. They all look the same. And after a while doing that kind of design, I thought, this is fairly constraining. It wasn't interesting me. And then I looked at satellites. Some of them have one solar panel, some of them have two solar panels, some of them have no solar panels. Some of them are cubes, some of them are spheres, some of them are squares. It was like fascinating. What drives all these shapes? It sounds very juvenile in a way, but to me it was fascinating. How come we have the freedom to do all this? Of course, there's no road, so you don't need the 4 tires on the road. There's no gravity. There's no real up or down. There's no aerodynamics. So you can pretty much build the satellite however you want to based on other constraints, like where do you want the aperture to point? How much aperture do you need? Are you very concerned about thermal? Therefore, you're going to build a sphere to minimize. Okay, so all those things, right? But when you launch on a rocket, the rocket tells you what your shape. All that freedom has basically gone away. Then the fact that you're in space at zero gravity doesn't save you from massive amounts of mass and energy and money spent to make the structure strong, because for 2 minutes, you have to survive an environment that hardly anything on Earth has to survive. The launch environment's much worse than bolting your radio to the dashboard of your car and driving over an unpaved road. That's nothing compared to a vibration test pre-launch. So there's the vibration. There's the fact that mostly for small satellites, you want to launch with the batteries discharged. So your whole reliability story is changed because you have to have a way to charge the batteries before the satellite is even alive in space. So all these little things creep up at you. Okay, what about the orbit insertion? Oh, I want to be in, sun synchronous, right? Well, the launch vehicle can't really deliver you into sun synchronous. They deliver you into sun synchronous plus or minus. So then you have to have a propulsion system on board to take care of the plus or minus. So all these little things contribute to we design the satellite to be launched. Tell me what the launch vehicle is, I'll design the satellite, right? Then the whole mission design, right, becomes affected by that. You can't have low-cost missions because you don't have low-cost launch is the obvious one, right? And then, like I said before, many missions don't exist because we don't have re-entry. I want to launch fruit flies into orbit. I want to see how their DNA is changed in the orbital environment. And oh yeah, I know I could do all this remote sensing, but it's fairly tricky to do. Just bring me the fruit flies back and I'll do the DNA analysis here on the ground. You can't do that, right? We can build a satellite. And maybe this is the key point. You can build a satellite on the ground in your office, in a lab of a bunch of students, but you can't launch it in your office. Sooner or later, you have to submit to the big infrastructure and go through all the qualifications and all the safety and all the structural and all the, will it fit and how much does it weigh and all that stuff. So unlike the PC, where you can just build the PC in your basement if you want to, and then use it, with a satellite, in the satellite case, you build it, but sooner or later you touch the space infrastructure, and the space infrastructure imposes all of its rules on you, so you don't have hackers. We don't have satellite hackers, right? The only people who build and launch satellites are working with the establishment, not against the establishment, right? Okay, so let's get off that subject totally and talk about something different, which is scaling, but not scaling of rockets, not scaling of the Queen Mary to the Boston Whaler, not scaling, of Learjets to 747s, but scaling of management, right? Because to me, not to build up any kind of suspense about this, the definition of small satellites is much simpler than we need to make it. The definition of small satellites is you can build them in a group that's very small. It's the people that determine whether the satellite is a small satellite or not the satellite. It's not whether the satellite is a CubeSat or launches on a Pegasus or launches on blah, blah, blah. I don't care. Tell me how many people it took to build the satellite, and I'll tell you whether it's a big satellite or a small satellite. If 5, 8, 10 people, 12 people can build that satellite in a year or two, it's a small satellite, period. If it takes 20, 30, 50, 100, 1,000, I worked on a project that had 10,000 participants. The mailing list had 10,000. I don't care how small it is, it's not a small satellite, right? Once you realize what the difference is that makes the satellite different because the organization is different, it simplifies quite a bit what we mean when we talk about a small satellite. Because a small group of people working for a short amount of time is incapable of building something very complicated. So not only have you simplified the management structure, but by force, you've simplified the technical structure of the thing. And that's really what the small satellite is. It's a simpler version of something that flies into space, whereas a large satellite is a complex realization of something that flies into space. So what's the magic of a small group? What's the magic of having 10 people working on a satellite is what this slide is really about. Well, let's talk about what's not magic about a group of 10,000 people building a satellite. A new component comes along and you want to use it, a new type of cutter for releasing a radio antenna, or a new type of antenna, and you want to use, oh, this antenna, it's smaller, it's lighter, it has more gain, it's all these advantages I want to switch. So it's not on the approved parts list. Before the program started, somebody went out and decided what are all the parts that are qualified to fly on this mission, going back to the risk problem. If that thing is not on the approved parts list, you can't fly it, but why not? I know that it works. I know that it flew on a previous mission. In fact, it's been used in space. So therefore, what are you going to do, right? Are you going to take your idea to the program office and get the person who's in charge of 10,000 people and a budget that's flowing out at a rate of $100 million every quarter of the fiscal year and get him to listen to your pitch about why this antenna is better than that antenna. And anyway, they've already given you the mass budget, the power budget, the X, Y, Z. Just do it, Rick, and don't worry about it, right? And then if you did get to change the antenna, you would change everything, right? The attachment is different. So the mechanical engineering people have to get involved. Oh, we have to make a different attachment for it. And what are the loads of that new attachment? Because it's now 2 bolts instead of 3 bolts, or it's this instead of that. And then what are the thermal interfaces? How rigid is it dynamically when it's folded up and when it's, okay? So now the guidance and control people, the flight dynamics people have to get involved. And then what's the thermal behavior of this thing? Because it is a different shape, it intercepts more sun or less sun. It has a different shadowing effect on the solar panels, therefore the power people have to do in advance. So what was the small amount of money or mass or whatever that you said you wanted to save by changing that? It's just like completely washed out by the system implications of making even a very small change. So you can say that about anything that happens to you during the course of the program. You're the guidance and control group, right, which is already hundreds of people, and you have an allocation, 10 watts, 10 kilograms, right? And you're being very innovative and you come up with a system that only uses 5 watts and 5 kilograms. So then what do? Go to the program office and say, hey boss, I can give you 5 watts back. Fantastic, right? And he's like, okay, what do I do with that 5 watts? I mean, you know, change the whole power system around. When the satellite is already designed, go back through all the design reviews. So there's a certain rigidity, right? And if you did want to make a change, you would have to communicate that change to 10,000 people and confirm that each one of them took time out of their day to think about, okay, if Rick makes this change, how does that affect my system? So this lack of communication, what I call the Chinese army form of management, where you have the blue box on top, which is this program office, and then you have all the different specialty areas, and underneath them, eventually you get down to the pink boxes and the green boxes that are like mechanical design, vibration analysis, thermal design, you know, flight dynamics, control system design. None of those people are talking to each other. There's the interface control document. They each have an interface, and they just work to that interface. And they don't, every day, the thermal people don't meet with the guidance people to see, well, if I make this change to the solar panels, how's it going to affect the stabilization of the satellite? By contrast, how does it work when you have a small team? That's really what I'm getting at. In a small team, let's say you have 7 people. Okay, you might still have a manager who's in charge of those 7 people. You could picture that in what I call the star diagram that's in the upper right of the view graph. Every person on the team talks to every other person every day. They meet for lunch, they're wandering into each other's offices, they may all share the same office. You make a decision, hey, I want to use this processor instead of that processor, then you have to talk to the guy who's doing the memory and see if you can interface with it. Probably that's the same person, that's probably also you. So there's really no interface problem because you're actually doing the whole digital system yourself. There isn't a memory guy and a processor guy, which is really a memory group and a processor group. It's all in your mind. If you decide you want to do it, you do it. So at that level, the change is trivial. If it turns out that that circuit board, that circuit card has a different aspect, the guy who's worrying about housing that card into a chassis is probably sitting right next to you. So you can just say to him, look guy, if I make this size instead of that size, is that a problem for you? And he can say, it's not a very big problem, I can do it. How much benefit is it to you to make the change? And you can say, well, it changes everything. I get this savings, I get that savings. This other part wasn't really available. We're going to have to ask the vendor to make a special part for us. It could hold the program up. On the other hand, this is available off the shelf. I can get it tomorrow and have it here. And he's going, fine, because it's going to take me a day of my time. So these little changes, which happen minute by minute, literally in a real program, or at least hour by hour, are very smoothly and easily managed in a small program, whereas they're impossible in a big program. So when the guy comes in and says, you know that processor that you spec'd back at the CODR or CDR and said you wanted, we don't make that processor anymore. So what do you say to that person in a big program? What you say is, I'm sorry, I have to have that processor. The whole satellite was already designed. The design was approved. That's the footprint. That's the power budget. That's the I/O. I must have that board. And the factory will say to you, well, okay, we can do that, but it's going to take N number of months and N $100,000. And you're going to say, fine, just do it. Because to change an organization of 10,000 people and go through all the re-reviewing is so much more expensive. You're not going to do it. And that happens in a small program. You just say, okay, give me the specs on the new thing. And you ask your office mates, can you handle this size instead of that size? They'll mostly be fine with it. And it's done in 10 minutes. So it's a totally different dynamic. And the other thing that was attractive to me, just to say on a personal level, having been a guy who grew up in the world of sports, and most of us do, or if you don't grow up in sports, you grow up in a family, these are small organizations that are exactly operate that way. When you run a family and you're going to have dinner together, you don't have to make an interface control document and a management structure and determine formally who's going to do what and at what moment it's all going to be done. It flows naturally from the communications among all the people involved. Imagine how a soccer team would work if the goalie could only be the goalie and could never leave the goal box no matter what. So the whole team would be locked into a certain way of operating. Unfortunately, that's how you have to manage when you're managing a big program. So if you're managing a small program, you have that flexibility to make changes and to accommodate new ideas and to look at a part that's never flown in space and say, can I use this part? And talk to every single person on the program. If I use it, does that fit with this constraint? Does that fit with this constraint? And people say, how is it possible you small satellite guys are using terrestrial components? And one of the answers is because we have the luxury of being able to think about it and decide whether that component can really work in this application or not work. We're not constrained by a certain formality of these are the parts that you can use and those are the parts you can't use, and there's no way any one engineer can possibly know all the constraints that a large system has to function under. And like I said before, the other difference is by artificially constraining the team, you could say artificially, to the number of people who can basically have lunch together, which is 12 or 14 or 15 or something like that, you automatically limit the complexity of the satellite, and that has other implications for the design of the satellite, which I'm just about to get into. So let's talk about scaling from another point of view, more concretely now, small versus large approaches to power. Because as the satellite gets smaller, the way you manage the solar energy that energizes the satellite, that powers the satellite, changes. And why does it change? Everybody who ever studied heat transfer knows how that happens, right? As something gets bigger, the surface area gets bigger according to the characteristic dimension squared, right? So the area grows as the square of the linear dimension, and the volume grows as the cube of the linear dimension. The volume is what's inside the satellite, right? So what's inside the satellite is electronics that needs power, right? And the area dimension is the aperture of the satellite. How much solar energy can I collect if I don't have deployable solar panels? As the satellite gets bigger, the volume is growing like the cube, but the area is only growing as the square. And eventually, the demand for electric power far outstrips the supply of electric power, so you need deployable solar panels to artificially create more area, right? So you could say that in reverse. As the satellite gets smaller, it has very, very little volume, but it still has quite a bit of area. And that's exactly what happens. When you look at a satellite picture, like the satellites on this slide, you can tell without knowing how big they are that the little spherical one with no deployable solar panels must be little. And the other one, which in my slide looks little but has these big deployable solar panels, must be a large satellite because it's lacking for surface area. So the fact that we have tons of surface area simplifies the satellite because we don't need deployables. And that, of course, changes a lot of things about the satellite. If you don't need deployables, you don't need mechanisms, you don't have changes in the CG, the center of gravity, you don't have dynamic effects of solar panels that may not exactly be very rigid, you don't have the thermal effects of taking the power collected over a huge area and concentrating it inside of a small volume. So you don't generate the thermal problems in a little satellite that you generate in a big satellite, in a big program. So this is, one of the simple ways that when you scale something smaller, the problem becomes much simpler. On the next slide, I talk about scaling heat transfer, and to sort of not walk you through all of the equations here, basically, if you look at the heat transfer equation, the amount of gradient that you can support in temperature between the hot side of the satellite, let's say the side of the satellite and the sun, the side of the satellite in umbra of the rest of the satellite, or the side of the satellite that's facing to space, goes like the length. So the longer the satellite is, the larger that gradient is. And the smaller the area of the structure is relative to that length, the greater that gradient is. And of course, what's not in the classic heat transfer equation, it depends also on the conductivity. So when you go from aluminum to carbon, you increase even more that gradient. If you do the scaling argument for a satellite with a length scale of 0.5 meter and a length scale of 4 meters, so about 8 times bigger, you end up with a ratio of the expected thermal gradient of 50 to 1. So that means a big satellite could have a gradient across the satellite of 100 Celsius or 100 Kelvin. The little satellite will have a gradient across it of 2. And a gradient of 2 is not worth worrying about, and a gradient of 100 is a disaster. So the thermal problem of building a very small thing, when you think about it, if the thing is small enough, it has no gradient across it at all. It's just a little block of aluminum. The temperature is uniform throughout that block. As it grows, it becomes more porous as a structure, and it has a larger length scale and bigger areas for the sun to irradiate, it's going to have a much larger temperature gradient on it. So from the thermal designer's point of view, the small satellite case is also much simpler. From a radiative point of view, which is the only way the satellite temperature is governed by the outside environment, because conduction is really an internal process, a small satellite in low Earth orbit has a radiation view factor of the Earth of about 50%, which means that it can not very much vary its temperature away from the Earth temperature, which is about 10 degrees Celsius, about 283 Kelvin. And what that means, and the satellite is very limited in power because it has very little aperture. So if the satellite tries to warm itself up, it will immediately start losing heat to the Earth. And what you find is if it warms itself up even as much as 10 degrees, the amount of power that a typical half-meter satellite loses to the Earth is greater than the amount of power it can generate with its own solar panels. So there's no way a small satellite can be 10 degrees warmer than the Earth. It's a physical impossibility. And it's equally physically impossible for it to be more than about 10 degrees colder than the Earth. Okay, on average, right? There are transients. While the satellite is in the sun, it could get warmer, and while it's in the shade, it could get colder. So you have, with a small satellite, the only thing we really worry about are the transients. But the steady state temperature is pretty much locked into Earth temperature, and that's not true of a bigger satellite. But there's a scaling argument that's maybe, okay, those are all interesting little physical arguments about mechanical engineering, but the one that is more gripping to me, more subtle, more gets into the soul of the design of the satellite is the reliability. Because, to put it fairly simply, on this slide on reliability, if you have a 99.9% reliable part over the life of your mission, whatever it is, that means that if you have one part, your mission is 99.9% reliable, which is really pretty good. As a matter of fact, if you have 10 parts, your mission is still 99% reliable, which is still pretty good. And if you get to 100 parts, you're at 90% reliable, because the reliability is the probability of every part failure multiplied together. So 0.999 times 0.999 times 999 times 0.999. Okay, done that 100 times, you're going to be at 90%. At 90%, you're not comfortable anymore. I have a 10% chance of the mission being failed because of the failure of a part. That's probably not acceptable. What do? Okay, you go to 99.99% reliable part, which is my red slide, and that pushes the horizon out. Instead of getting limited at 100, you get limited at 1,000. As long as my parts count's less than 1,000, okay, if your parts count is 10,000, then you need a 99.999% reliable part, and so on. Okay, parts weigh what they weigh, right? So when a satellite goes from weighing 1 kilogram to 10 kilograms to 100 kilograms, you're multiplying the number of parts by 10 every time you go up an order of magnitude in the mass of the satellite, more or less. And what that means is, in a little satellite, parts don't fail. Part failures are not your problem. In a very big satellite, parts fail. So the failure mechanism of a small thing is totally different than the failure mechanism of a big thing, which, I mean, changes everything, right? So people want to know, gee, Rick, how do you guys get away with flying those terrestrial parts on your little satellites? Parts are not our problem, right? We have other problems, but parts are not the problem. You guys who have 1 million parts on your satellites, what do? You can't get 99.99999% reliable parts, so you have to have redundancy, right? Because you know that some of your parts are going to fail, and you know the mission has to go on after that part fails. So, okay, I have 2 radios, I have 4 momentum wheels, I have 3 or 5 computers to decide which computer has failed and take that computer, and you end up with this incredible complexity to have redundancy, and you limit the design because you're limiting yourself to parts that have proven 99.9999% reliability, which means you can't get them on the commercial market. Every one has to be a space part. And that accounts for some microscopically tiny fraction of the processors available in the world, of the resistors available in the world, of the switches available in the world, of the connectors. You are living on a little island, completely isolated from the mainstream of engineering design, in order to specialize in those parts that have 99.999999% reliability in the space environment, which eliminates everything. Okay, on the other hand, the small satellite guys are flying commercial processors stolen out of smartphones, and the same connectors and everything else that is in the exact mainstream, batteries, lithium-ion batteries, all kinds of stuff that we're flying is like totally unacceptable in the large space world, in part because they don't have the decision-making power to evaluate every one of those little parts piece by piece in a gigantic program of tens of thousands of people, and in part because they have a different engineering problem, which is to ensure the reliability of a thing that's composed of millions, probably millions of parts. Whereas we guys building 100-gram satellites have one part, a chip. That's it, that's all you have. So even if that thing is really crummy and it's 99.9% reliable, it's not going to fail. I have to look elsewhere for my failure problems. And that, I'll tell you, is really important. I was at a design review of a satellite project, and the NASA reviewer said to me, Rick, are you trying to tell us that the satellite will be more reliable if we build it with less reliable parts? And I knew that I was going to give him not the answer that he wanted, but I was sort of constrained to give him the answer that was the right answer, because that was in fact the approach we were taking. I had to say, yes, a satellite built with less reliable parts is more reliable. It sounds insane. How is that possible? Because using those less reliable parts, quote unquote, allowed us to use more modern parts, so we had less parts. So the probability of failure, the number of 9s after the decimal point, can be less because we're taking that to a lower power. We have less parts in series. The other reason, which is even less appealing to engineers, is that we had a fixed budget. So every dollar that I spend on a part is a dollar I cannot spend on engineering, or I cannot spend on testing. So let's go crazy and spend every dime, every penny of the program on parts. How reliable is a satellite going to be? 0 engineering, 0 testing. Okay, that's obviously not going to be a formula for success. So we'll minimally fund a very tiny engineering group that has no time to do all the analysis required and is so buried in paperwork that they really do a very superficial job on the design. They work until the very last minute and they drive the satellite to the launch site having never really tested it. How reliable is that? So in fact, we all do that. We all steal money. We'd love to spend $1 gazillion on parts and have perfect parts. But unfortunately, the perfect parts are way too complicated, and we don't have enough money left to do the design and to do the testing and to do all the other things which are not there for fun. They're there to make sure the satellite actually works. So I would say save money on parts. In a small satellite where parts are not your problem, spend it on testing. Because you're building something that's never been built before, never been tested before. It's not like human beings, we got 6 billion of them out there. We know what makes human beings fail. Your satellite, when I've worked on satellite failures, it was never the thing we thought about. It was never the thing we worried about. It was some crazy thing. How do you find that crazy, unexpected thing? You just test, 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 test. But if you spent all your money on parts, you can't afford the testing, and so you don't do the thing that's the most and historically proven to be the most effective in raising reliability, which is testing.